Okay, it's 7:04. We'll start the today's discussion session, mainly based on the problem solving session. So last time we actually discussed about how my molecules become the CD active. So for that there is some intrinsic property which is present in the molecules, which can actually provide the ability to absorb chiral light, that is LCP or RCP, in a different absorbance, which makes the uh, different molar extinction coefficient for the different light, and that creates the ellipticity. Okay, so basically where we actually, let me recapitulate these things. So we have our circularly polarized light, where our molecule, one of my molecule over here, this is the molecule, where molecules is present over here in the solution. We have the RCP and the LCP. They have their different absorbance in the solution phase, and where the we actually taking care that this absorbance is RCP is lower in the solution phase, and the LCP mainly absorb the LCP. As a result, we got a electricity, and from it we can show the circular dichroism spectra of that molecule. And on other hand, if the light gets slowed down, that means if light actually facing the uh, different speed in the solution phase, that means different refractive index in the solution phase, then it's show the optical rotation. That is the as a result we got the circular bifringes. Okay, so and then we talked about how what is the intrinsic property which is present in the molecules, which actually responsible for the uh, CD optical activity and CD spectra. But we found that in the CD spectra there should be some absorbance, and which is absorbance of the chiral molecule, and with respect to it we got the ellipticity, and then in that molecule, which is that there should be some magnetic dipole moment, and the electrical dipole moment, which is present, which is supposed to be present, and that will be each and every magnetic moment with respect to their rx and rx direction, which is actually perpendicular to it, and as a result rx and x, which makes a helical motion, and that helical motion actually provides the chirality inside the molecules, and the handed circularly polarized light, or circularly polarized light, that also a elliptical propagation, and both the helical motion interact to each other. Once a time it may absorb the light, or interact, the particle molecules interact with the lights, and sometimes it absorb the light, sometimes it slow it down the our light, circularly polarized light. Basis of that we can provide the idea with is it optical rotation, or is it circular dichroism or ellipticity. Okay, so and then we actually talking about the molecule, which kind of molecule uh, actually active in CD and optical birefringence, circularly birefringence spectra. So to check that, we actually found the molecules in the point group. With respect to that point group in the character table, the mathematical character table of that molecules of that point group, where the both x rx or y ry or z rz, they must active together in a one particular symmetric operation. That may be double degenerated E operation, that may be anti-bonding A2 of A2 orbital, that may be A1 orbital, that may be D orbital. It's depending on their point group. They're supposed to be present in a one particular symmetry operation. Otherwise, that molecule will not active in optical activity. I will not show the any optical activity. That that may be your optical rotation. That may be your uh, CD spectroscopy. Okay, so to check that, we actually took some example. One is the D4 rays, where we found there is no symmetry operation, which is that is any symmetry operation like A1 A2 A1G A2G B1G B2G EG A1U A2U B1U B2U EU sigma pi, all those orbitals or symmetry operation, they don't have in a one particular symmetry operation, where my RZ or RZ and G or RX or X RY and RY Y and RY simultaneously active together. There's some certain point where that Rx and Ry active in a EG, but X and Y active in EU. Both are the different symmetry operation, and one case A2G for the RG is active, and the A2U for the G is active. Both are in different symmetry operation. So in that case, we this molecule is not active in CD spectrum. This is fundamental thing is that in one particular symmetry operation, where my X and Rx or maybe Y Ry or Z Rz, those are active together. Otherwise, there is a missing of the magnetic dipole moment or electrical dipole moment. If those are not active, then there is a no chances of molecular helical dipole moment, molecular helical motion. That is the dipole moment motion of the molecular which is the molecular intrinsic property. So for that, we need at least they should active the there should be active of X Rx Z Rz or Y Ry in one particular symmetry operation. Okay, and then we got another example where the molecule is D3 operation, a D3 symmetry point group, where we found A2 has present ZRZ, one particular symmetry operation, and E contains X Rx Y Ry together. Then it becomes where the mu E and mu M are active in that case, and then that will provide the helical motion of dipole moment with the help of the electrical and magnetic dipole moment, and that will becomes the is optically active molecules in CD as well as the in the circular bifringes CB. And so with respect to all those point group and the character table, where we only find where that molecules having point group on and only Cn and Dn point group, which is active in CD activity, CD or optical activity. Okay, so our our discussion first point will be molecules having point group CN and DN point group will be optically active. One interesting point is this N can be defined as N should be here N greater than equals to 1, here N greater than equals to 2. Otherwise D cannot be, if D at least should be 2, otherwise there should be some C2 will not present. If it is 1, there is no chances of D, because of for the D we need at least 2 perpendicular C2 at with respect to the C2. If C1 is there, there is no chances of the C2. If molecule having the C1 only, there is no chances of the C2 then. So that time D will not applicable. That time we can say only the C. Okay. So this is our major fundamental factor. And the character table, which is another star point, will be molecules having X, Rx, Y, Ry, Z, Rg, any of them active together in a any any operation that should provide the active of mu E and the mu M together, which will actually provides the helical motion of dipole moment, molecular dipole moment. And which will interacts differently with LCP or RCP, or not, or will be and and behaves different, become optically active. Okay. With respect to which we actually discuss about some result where that we found we introduced some cotton effect, how the cotton effect actually works, where the molecules having the highest absorbance at that wavelength, where the my optical cotton effect will be zero. That means my uh, theta, phi will be zero. Because of that, in that particular wavelength, my molecules absorb all the light, and then there is no chances of passing through another some lights. So in that case, we cannot get any optical rotation. And this and that's how the CD spectra, if the molecules having the, and another interesting point is that the plane curve, which is actually found in the optical rotation in the circular birefringence, where the molecule is not absorb any light in that region, there we can find the plane curve. And with respect to it, we can actually generally, in a sucrose solution, we determine the optical rotation of the sucrose solution in that particular plane curve region. And the CD spectra, fundamental is that molecule have to have absorbed the light in particular in that particular wavelength region. So if there is no observance any particular wavelength, there is a no question of the any optical activity, any CD activity. And interestingly, molecules uh, having different observance in a one particular molecules, maybe they have a four different soldier, but molecules only active CD activity, show the CD activity on one or two or three particular uh, active region. So one example, we found that there is a four harm solder kind of things in the observance spectra. In the CD spectra, where we found that one or two harm are actually active in the CD activity. So one of enantiomers show the one kind of CD activity, another isomer can show the exactly opposite of mirror image of the CD activity. Okay, and finally we stopped here, and then today we actually going to discuss some other examples. So coming to that, with that there is a one molecule. Let's try another molecule, which is, let's suppose we have the C2V point group. We have example is that molecules. Let's try with the molecules. There will be manganese. We have some mardanal, C over here, C over here, beer, and that will be beer, should be beer, and that will be my beer. C. Let's find out the point group. point group. The point group is C2V. Will it be optically active? Let's find out the character table. Okay. In the you don't have right now. Let's check the character table. Okay. It's not opening. So we are pressing. So as it is C2V point group, as it is C2V point group, there is a no chances of activity of activity of X RX Y Y RY Z or Z active simultaneously or on one particular situation. There is no chances. There are also no chances. There is no chances. So not active in CD spectra. Okay, similarly, we have the ligand of we have the cobalt over here, another molecule, cobalt over here, we have ethylene diamine, and, and, and these are the this is N N this means my NH2 and this will be my NH2. Okay, and let's find out what is the point group. Point group will be point group will be what is D3. D3 means we said that the point group having the only CN or DN, then they are only active in CD activity. So this is also active CD active. Okay. So and then now our question will arrive. We have optical rotation. Optical question is that Q. We have chiral molecule. Chiral molecule. and we have two technique to detect the chiral molecule. One is the my optical rotation, optical rotation. Another will be my ellipticity. So which one will be the more reliable? Now question will be the which one will be the more reliable. Now coming to the optical rotation, we have something like cotton effect. Anything else. We have optical rotation of Perseus, negative cotton effect. Similarly, positive cotton effect. Okay. So these are the cotton effect we can found in the optical rotation experiment. And whenever we are doing the optical rotation measurement, we are doing the each particular point, one certain point. In that point, there is a no optical rotation we will found. If we try to, it is so so in that case, if we try to find out the optical rotation, whatever we don't know the molecule. Initially, we don't know the molecule. We will try to find out the optical rotation of that molecule in a one particular wavelength and one particular temperature. So we don't know the absorbance of that molecules. We try to find it through the optical rotation, which is actually chiral or not, the molecule is chiral or not, and we found no result. There is no optical rotation because of, oh, okay, this will be my theta. Oh no, phi. We are talking about the phi. This will be phi. So don't find any, and sorry, everything should be written. So we don't find any optical rotation because of there is a chances of the my optical rotation which is actually measuring at the point where my optical rotation found to be zero, at that cotton effect, because of that cotton effect. So we can say that the optical rotation is applicable when if we know the absorbance of the molecule. Otherwise, if we try to find out the optical rotation without knowing the absorbance spectroscopy, there is a chances of wrong interpretation of our data. Okay, so maybe if we want to find, another point is that if we want to find the, if it is uh, D or S or Ri isomer. Let's suppose we took the L isomer. Sorry, we have a D glucose and L glucose. There we took the D glucose and try to find out through the optical rotation, is it D glucose or L glucose. So, as we know, the D glucose should rotate the light in a clockwise manner, and L glucose should anti-clockwise manner. But there is this one certain criteria. So we have to provide the wavelength. Otherwise, it will show the cotton effect in one particular wave. After the one particular wavelength, D glucose may show the my reverse optical rotation. That is, if it is showing the clockwise rotation, it may show the it will show the, after the cotton effect, the lower region, it will show the my negative optical rotation, that is anti-clockwise optical rotation. Okay, so there is also sensitive towards, very much sensitive towards the wavelength, as well as if we change the temperature, that we know the optical rotation is a in a basic fundamental of the defined of different uh, refractive index of the light in a solution phase by the molecules. Uh, so my molecules actually provide the any physico-chemical condition where my my light should, so left hand circularly polarized light and a right hand circularly polarized light will face the different refractive index and define they face the different speed of the light. So if my certain changes of the temperature, pH, any physicochemical condition, pressure, any physicochemical condition, it will hugely change if show the effect on the refractive index. As a result, we found a huge changes in the optical rotation. We will definitely find different cotton effect in that one particular molecules in a one particular solution, as well as the if we change the solvent also, that can also give the any different result. So this is very sensitive towards the in this optical rotation is very sensitive towards the physicochemical condition. So point is that optical rotation is the very sensitive towards the physico-chemical condition of the molecules or solution. Okay. Now, on other hand, if we talk about the CD spectroscopy, we have the electricity kind of thing, psi and wavelength plus minus psi is, which is actually associated with the my absorbance. So as we know, the absorbance changes with respect to the physicochemical condition, a very slight effect. It has a very slight effect. Not, it has a effect, but it is not that much change. If we change the pH, if molecule remain in a same, let's suppose we don't have any proton exchange kind of thing in that in a one particular molecule. We have some molecules, they can change their proton and show the different UV spectra. That is the different thing. If molecule doesn't change the any proton effect or any other thing, if we change the temperature, if we change the pH, it doesn't have certain change of that absorbance in a one particular wavelength. There is a change, there should be a change, but change will be very different and very less, and which effect doesn't follow up in the circular dichroism. So it is less sensitive towards the less sensitive towards physico chemical condition. And whenever we are doing, one interesting thing is that when we are doing the CD spectroscopy, before that we always perform the UV spectra, so we able to know the where our band will come and where the band actually active in that particular wavelength region. With respect to that, in that CD instrument we provide the region from where to where we should scan in particular time. Okay, so this is the thing we have to fundamentally use, or CD spectroscopy over the optical circular bifringes uh, experiment. So CD spectroscopy is a very much effective towards the identification of the one particular isomers. So we can use it anywhere for the chirality will observe. Okay. Now some we'll look forward to some example. Example will be in our biological system, that is called protein. In the protein, they have four different structure. One structure is the primary structure. Primary structure, which is how it looks like. We have some C double one O. C, this will be the chiral module one. We have the N, H, and followed by here is the NH amide bond. We have C, we have C, bond O, same, and NH. R1 or 2, and this will be my C, R3, C, this is called, this is the primary structure of the my, this is the amide bond, this is the peptide bond. This bond is called peptide bond. We can use a different color. This is peptide bond. This bond is called peptide bond. So this is connected with the, so all the amino acids actually connected with the peptide bond. This terminal is called N terminal, and this is called C terminal. Okay, this is the primary structure of the, we have over here we have the amide bond. Amide bond, this is called peptide, actually called peptide bond. This is also is followed by, this is the peptide bond also be there. So this is the primary structure of the uh, my my protein. We have another structure which is secondary structure. Second structure is the protein is secondary structure. We have lots of group associated with that chiral carbon of the amino acids. That may be my protic OH group, or any sulfur containing cysteine group, or any um, basic group that is the lysine, all those things. So we can this group actually interacts with the nearby any other amino acids and provide a 3D structure of the one kind of 3D structure of the amino acids, that may be helical in structure, that is the called alpha helix. If it can create a seed kind of structure that is called beta seed, and sometimes it may be there is no chances of any structure that is called random coil. So we have some data, we have some structure over here. We can where it is, and show it. Okay, so this is the structure. In the next page we have, this is the structure. This is the structure where this is my, we have our primary structure is that carbon nitrogen CO, carbon nitrogen CO, carbon nitrogen CO. This is the primary structure we are talking about. Now this NH, this amine NH has one hydrogen bonding to nearby another strand of that peptide chain. That is, that's how this propagation happens continuously and make a seed kind of structure. This is called beta seed. And it seems to be my, it started with the C terminal and end up with the end up with the N terminal. So reverse side also similar, not reverse, on that reverse side. So this is the anti-parallel beta seed. If this peptide chain similar to this peptide chain, it called parallel beta seed, and this is the anti-parallel beta seed. Now we have the one interesting is that if the peptide is actually forming the helical kind of structure where this hydrogen bond actually uh, hydrogen bonding happens through a nearby any protic group, that is the amine group, and that carbonyl group are the amide. They have a um, different interaction between this hydrogen bonding and this hydrogen bonding, and that will give you the different result in a series spectroscopy. Will come into the later part. So these are actually showing a, that can create a helical kind of motion. If I my protein structure very not this kind of structure, then it called a random coil. So if we heat the protein structure in a certain temperature, there is a increasing in my entropy factor. And if we, as we increase the temperature, there is a extra enthalpy we are actually providing to the molecules, which is actually suppress that enthalpy which is found in that hydrogen bonding. This is the hydrogen bonding. This hydrogen bonding can be compensated by external energy. So in that case, we only get the random coil structure, and they have a defined CD activity in the in the CD spectrum. Okay, so this is the my alpha helix and beta seed. We have the random coils, that is the randomly oriented. So here you can see that this is the randomly oriented over here. This is randomly oriented or loops kind of thing. This is called random random coil. We have the beta seed over here. This is the green color is the beta seed, and the alpha helix is the red color alpha helix. We have the some loops over here, that is the gray color, and the yellow ball and stick is the bound molecule. Okay, this is the bound molecule we are talking about. We have that, we have the loop and turns over here, and random loop, that is the random loop and coils over here also. Okay, so in the 3D structure, all these beta seed, alpha helix, and random coils, turn, loop, all those things containing in there. This is the 2D structure. This is 2D. That is the secondary structure. Sorry, secondary structure. This is tertiary structure, and this is This is quaternary structure. All the this one kind of tertiary structure. This is an example of the hemoglobin. This is hemoglobin. In the hemoglobin, there is a four myoglobin kind of unit. They are actually interact connecting through the salt bridge interaction. And this is the purple color is the one unit, blue color is the another unit, green color unit 3, and red color is the unit 4. These four unit actually interconnected through the salt bridge interaction, and that creates a quaternary structure of the my protein. This is the quaternary structure. Okay, so how many structure we found? The four types of structure we found. One is the primary structure, second is the secondary structure, third is the tertiary structure, fourth is the quaternary structure. Okay, now coming to the main point, we have our protein structure, that is alpha helix or beta sheet. Okay, if alpha helix, you can there is a how many bonds are available in the amide bond, which is actually active in the UVB spectrum. So bond will be my, this is the C double bond O and NCN bond pi pi. So what kind of transition can possible? One is the N to sigma star of the NC bond, or there is a chances of pi to pi star, where the C double bond O pi bond, where the pi to pi star transition can possible, and there is a chances of the N to pi star transition. Okay, so three kind of transition is possible. So which is actually N to pi star is N to sigma star is very highly energetic. Pi to pi star is kind of visible in the UV 200, around 200 region. N to pi star is much lower in energy, a little bit lower in energy. So each particular, can we detect the this secondary structure of the my beta sheet or alpha helix or random coil of the protein through the CD spectroscopy? Yes, we can do it. So in that next can showing it that we have a UV spectra of, this is the first one is the UV spectra. This is the UV spectra of three different secondary structure. One is the alpha helix, second one is the, this is the alpha helix, this is the beta sheet, the random coil. Okay, so we have, this is the frequency region we are talking about. This is the 10 to power 3 centimeter inverse. If we calculate it, it seems to be similar in energy over here. So this is actually responsible for the my, this spectra is actually because of the one for the this lower in higher energy region. This is the higher energy region. This is because of the pi to pi star transition, and another is the N to pi star transition. It's similar to the beta sheet and the random coil, but there is some changes in UV spectra. This is not easy to follow it up. If we, can we go through with the CD spectroscopy? If we go for the CD spectroscopy, we'll get a different, exactly different say activity. So there is some characteristic over here. So first of all, come to the alpha helix. This is the alpha helix. We have here is the one is the black one is the alpha helix, where the one is that this is the 222 nanometer. We have in nano, we have a hump over here, and 208 will be the another hump, and there will be another hump around 193 nanometer region. This is the, this is positive. 193 is, will be the alpha helix. 193, that will be the positive. 208 will be in nanometer. 208 negative, and 222 negative. This is the characteristic of the alpha helix. Similarly, beta sheet in nanometer, we have a characteristic of 195 positive and 218 broad negative, and that will be broad negative sorry about that, broad negative spectra. So in that case, you can check this is the red one. This is the anti-parallel beta sheet we are talking about. We have a negative maxima around 218 nanometer region, and we have a another positive maxima where the region is the 195. So this is the characteristic of the beta sheet. Now we have a random coil. The random coil is a characteristic where we can find one characteristic is there. It will be the 195 where the negative, and the rest of the thing will be the defined. Maybe possible there will be a different kind of structure in a uh, in other region. This is the characteristic of the three different kind of structure, to secondary structure. Now, can you calculate with respect to how much is present? Yes, we can. We have to deconvolute the data, and we have to find out the actual what is that amount of the your alpha helix, beta sheet, or random coil present in that particular enzyme or protein structure. Now, question is that why beta sheet show only 218 region in broad spectra, whereas my alpha helix actually showing a two different shoulder kind of thing, a shoulder kind of spectra, for one at 208, another as 222 in negative region. As we know, 193 and 195 is the mainly because of the pi to pi star transition. That there is a n to pi star transition which is actually following up in 20 after the 200 nanometer region. So so why the beta sheet show one into pi star transition, and the alpha helix show two into pi star transition? Oh, so this is because of the my pi to pi star transition, and these are because of the my n to pi star transition. We have in the random coil, it also has the n to pi star transition over here. It is the very little amount, and that is the positive direction. And alpha c alpha helix and beta sheet has a negative at the negative direction, n to pi star transition. So why it is happening so? Now question is, so to answer that, we have to came back again the structure of the my alpha helix and beta sheet. In the beta sheet, if you can check, we have a transition where my transition is over this direction. N to pi star, lone pair of the my N and nitrogen and the pi star of the C double bond O. So we have uh, interaction, the anti-parallel, but their distance is similar. All the N to pi star transition or the all the hydrogen bonding between one peptide chain to another peptide chain are nearly similar. So this is the anti-parallel chain. We have the similar in hydrogen bonding distance. So it has a similar N to pi star transition. So, but if you check the alpha helix, if you can find, this is the, let's suppose this is the amino acid number, this is maybe 1. Let's talk about, this is the 1, this will be 2 and 3, this will be 4, 5, 6, 7. Let's talk about where the hydrogen bonding actually happening 6 with the uh, 6 with this amide bond of the carbon 1, amino acid 1, and another hydrogen bonding, in this particular region. We are considering this particular region. There another hydrogen bonding over here with respect to the amide bond of the carbon number 2 with the carbonyl group of the carbon amino acid number 3. So the distance is different over here, and here distance is hydrogen bonding interaction is distance is different. So these two amide bond has a some different amide hydrogen bonding interaction with alpha helical structure. So that's why this is a shorter hydrogen bonding, this is a very longer hydrogen bonding. So these two amide, this amide bond and this amide bond actually show a different interaction. So if there is a different interaction, there is a chances of the two different amide bond. So if two different amide bond is present and two different momentum will be there, and two different amide N to pi star transition is being present in the alpha helix. So but in beta sheet, all the distance hydrogen bonding distance are similar. In case of parallel, they are also similar. In anti-parallel, they are also similar. So we have a one kind of hydrogen bonding or beta sheet, and one kind of hydrogen bonding between the amide NH to carbonyl in beta sheet, and in alpha helix there is also two different kind of hydrogen bonding in the alpha helix. For the hydrogen bonding, we are considering about only the amide nitrogen, amide amine, and the carbonyl of the uh, amide bond. Okay, so so that's why we are finding two different n2 pi star transition in the alpha helix. In the beta sheet, we have only one. Okay, someone join or not? Okay, there's nothing, no one is there. So we have one into pi star transition is present. Okay, Srikant. Hi Srikant. Left. Okay, so as one into pi star transition is present in the beta sheet, so we have we have two we have one broad band around the 218, where the maxima is present, or 218 nanometer region. Okay, so this is the major fundamental CD spectra of the alpha helix, beta sheet, as well as the random coil. Okay, so now can we find out a uh, different different amount of alpha helix and beta sheet in present in the different protein? So to check that, people has been record different CD spectra. One of them is that over here we can actually showing the how should look, how my uh, alpha helix, antiparallel, beta sheet, distorted beta sheet, all those distorted, and collagen triple helix, collagen denatured, all those protein structure actually show the only that protein structure show the uh, CD. Okay, what happens? Okay, just a minute. It's because of the internet connection. Trying to log in. Hold on. Okay. Sorry about that. I lost the internet connection. Okay, come back again. I think this is okay. Okay, we are discussing about we have a some different alpha helix, antiparallel, beta sheet, distorted protein structure, as well as the collagen triple helix. We talk about that in a different class, in a to how triple helix can be possible, and the collagen denatured collagen, that is the different structure we have. So we have a alpha helix. There is a characteristic is that 222 nanometer region, 208, and the 193. Beta seed will be the 218 and the 195 positive. In the random coil, we have negative 195, the uh, maximum, and it starts with the positive. Initially it starts with the positive, and on certain, after a certain wavelength, it starts so the negative series activity. Okay, so we have some different protein over here. The myoglobin, one is the protein is the myoglobin, one is the LDH, and is the chro- chromatopsin, chromatopsin, sorry, chromatopsin. Sorry about that. My because of the my throat actually facing some issue. And Benz Jones, another is the Benz Jones. So with respect to it, they actually record the data of the CD spectrum. For in the myoglobin, you can see it starts with the to nearly about the alpha helical structure of all the protein. Actually looks like a alpha helical structure, but it may contain the only alpha helix or may not be contain the alpha helix. may contain the defined amino acids also, may define secondary structure also. Now coming to the LDAs, this is the two where that is showing a 2 over here. There is a maxima, positive maxima, and it's coming down a 2 kind of hump over here. 1 to 208, another is the 2 2 followed by a broad kind of structure over here. And then we have some the commutative scene has a different CD structure. Another is that we have over here also different CD structure. If you deconvolute it, people has been deconvolute with that with respect to the data actually available for the only for the alpha helix, only for the beta sheet, only for the random coil. We will deconvolute that. In that deconvolution data, we can full zoom in. This is the data. The myoglobin, and that myoglobin, they found this is the nanometer region with they are actually deconvoluting. Okay, in the myoglobin, they found that 96% of alpha helix is present. There are only rest of the thing is the trans, trans. That is the that is we are talking about. This is 200, 200. This is the 200. These are different pH and the different region they are actually different solution, pH solution they are actually taking out of it, and then they this myoglobin actually extracted in a uh, different different source. And there they actually found it different kind of amount of alpha helix and trans are present. There is no beta sheet actually present has been found over here. So only thing is that over here only they found little bit of beta sheet kind of structure. They has a different source over here. So in the lactose dehydrogenase LDH, that is, we found that the structure is different. We found that there is a chances of the 73% is the alpha helix, beta sheet is the 14%, and then my 25% only is the uh, trans. 25% is a trans, and the random calls is present over there. Trans and the random calls. So and the chemotrypsin, we have the alpha helix percentage is the higher. Beta seed will be the alpha helix is that only 10%. Beta seed is the 38%, and trans is the 26%. Similar to the Benz Jones protein, which is 3% alpha helix. Beta seed is the major part, 50%, and 24% is the trans. So that's why in that spectra we can found that the myoglobin actually showing a alpha helical structure because of that it has a more than 90% of the alpha helical structure in that myoglobin. And then LDH, lactose dehydrogenase, they have little bit amount of alpha helix, followed by there is a broad kind of structure, something 208 because of the alpha helix, and 202 for the alpha helix, and the 218 is for the beta c. And beta is and where the alpha helix is predominant, so that's why we are only getting the to hum over here, and is a one other broad kind of structure here to 18 nanometer region. So so this is the data they actually found with the help of the CT spectroscopy. This kind of data can be recorded anywhere, any kind of solution you can take, any kind of protein structure you can take. You just may record the CT spectra and deconvolute it with their actually provided initial data, actually already simulated data, and then we can deconvolute it. What is the amount of the alpha helix present in that protein? What is the beta sheet present in our protein? What is the random coils or turns or loops are present in the protein? Okay, so this is the another technique to I identify the my protein structure. There is another chances is the crystallography. Crystallography we can do it. but the crystallography only can provide the data where my protein is in ground state. That means a more stable structure of the protein we can identify through the crystallography. And if it is in solution phase, it can show different kind of data. So maybe they had a different state. Only stable state we can found in the crystallographically, but other state we cannot determine by the crystallographically. So we have to take another experiment where the CD is the major experiment to isolate my what is the amount of alpha helix, what is the amount of beta seed is present, what is the turns amount of turns or loops are present in that particular protein. Okay, so this is the advantage of the CD spectra. So another advantage is that we know the protein denaturation. Okay, protein denaturation where we have the protein is stable protein structure. Let's suppose we have a alpha helical structure, and then or beta sheet is present over there. Then we start the increasing the temperature of the solution, and we record the my uh, record the CD activity in the particular point. So in that case there is a uh, guadinium hydrochloride increase concentration. And this is the guadinium. This is the protein denaturation has been recorded in a different temperature, as well as we can do it in a different protein, different acid. So here this is the CD spectra cytochrome. Cytochrome is an enzyme. We have the cytochrome C, and we actually increase the people actually include guadinium hydrochloride, which is a different acidic solution. And in presence of this acidic solution, protein becomes denatured. This protein denatured with respect to the guadinium hydrochloride to for the increase of um, uh, solution concentration. Guadinium hydrochloride solution was 0 to 4%. So you can see there is a alpha helical structure over here for cytochrome, where the maxima is around 2 to 2 nanometer region, and they record the one, they fix the wavelength, and then they find out the electricity, and they each point each every amount of guadinium hydrochloride addition, and they record the data, and they found this kind sigmoid kind of data after a one per certain uh, particular concentration of the guadinium hydrochloride. There is a no certain change. There is a very less significant change. Only significant change over here from here to here in, and in that particular region we actually call the protein denature condition in particular temperature. Okay, so this is, they actually plot that temperature in that 2 to 2 nanometer region, and then they found this protein denature happens in that particular, that is around 1.75 uh, guadinium hydrochloride concentration region. Okay, so this also can be this protein denature where the my, and also similarly we can with respect to the temperature, we actually also can monitor the protein denature temperature, or with respect to the temperature. If we change the similarly, we change the temperature, and with the my alpha helical structure of the becomes the random coil to beta c to different different structure, which is actually also monitored by the CD spectroscopically. And then we can find the protein denature temperature, that is the melting point of the protein, we can calculate from there also. Okay, so to that there is another example where we, that is from our own lab. We have my cobalt complex. We try to find out that sensing oxygen sensing criteria. We develop some catalyst which is actually very much reactive towards the oxygen. So to that, our one of my group members actually did this experiment. He took the histidine molecule, which is actually chiral in nature. As we know, this carbon is the chiral carbon, this is the chiral carbon. So we have the chiral over here, and we have the cobalt over here as a metal, and it forms the deoxy deoxy cobalt, this complex, cobalt complex with the histidine. And then if you pass the oxygen, it will actually reversibly bind the oxygen, and that actually monitored by the UVVs as well as the CD spectroscopically. Okay, so as histidine is a very chiral molecule, and this molecules, this cobalt histidine molecules is become the chiral in nature. If it is chiral, so this is also chiral. So this is also chiral. So this cobalt, this is showing, it can show the my CD activity. So in that CD spectra, you can find where the my this is the deoxy cobalt complex, the red one. This is the red one. This is the deoxy, and if you pass the oxygen, that also reversibly bind the oxygen, and it will show the different LMCT as well as the LMCT. Because of the oxygen is bound, it is forming the cobalt peroxo bond. This peroxo also monitored by the Raman spectroscopy we actually found in a last month. And then this is LMCT actually increases because of that. This is the oxygen bond is forming, and they're showing a different orbital structure, and then so this LMCT actually arises, and this cobalt actually becomes the cobalt 3. But this certain change we have been found. But if you check the CD spectra, there is a huge change in over oxy cobalt oxy cobalt histidine complex, where you will find that it starts with the 700 nanometer region. It is a positive, and then it starts this DD transition becomes a chiral. It was not able to found in that case UVB spectra, but in CD you can see there is a hum over here. It's very much, it is found in that in the city. And then we have the maxima over negative maxima over 500 409 485 nanometer region. Again, it's again rises to uh, maxima has been found 390 nanometer region. So this phenomena actually monitored in the UVBs as well as the CD spectroscopically. So CD actually showing uh, showing a different kind of structure which is found in the in presence of the oxygen. But similarly, this oxo species actually again return back to the deoxy form while we purge argon or nitrogen into that solution. Okay, so this is phenomena has been also recorded by the CD spectroscopy. Now, question is that what else we can do? Okay, so there is a one ligand. This is the called RR diamino NN disuccinate. This is a succinic acid, salt of the succinic acid, where the succinic acid is the R and R form, and another form is the S and S form. So how can we differentiate these succinic acids? But it is very easily by the series spectroscopically. We have some we have a UVB spectra of this uh, succinic acid. Uh, it will show the similar kind of structure. If you make the cobalt complex of these succinic acids, then it will form two different kind of isomers. One with the cobalt succinic acid complex with SS isomer, and another is the RR isomer. all those succinic acids are in chiral in nature. They are actually inducing the chirality into the cobalt center, as well as we found in the CD spectra, we have a DD transition over here and the other CD activity around around 200 nanometer region. This is because of the into pi pi star transition of the pi to pi star transition of the C double bond O, which is actually also found in the protein structure, where the pi to pi star transition has been found in the C double bond O has been found in around 195 195 or 90 to 95 nanometer region. Similarly here, the around the 210 nanometer region, where the my all the succinate C double bond O pi to pi star transition has been found. So this DD transition in the UVBs do not see any kind of certain change for all the all the isomers, RR isomer and the SS isomer. Okay, but in the CD you can find there's a two isomer actually so behaves in a different structure. So one for the SS diamino one, another is the RR diamino one, will show the different CD activity. So from where we can isolate that one is forming the SS diamino NN disuccinate with cobalt 3, and another is the RR diamino NN succinate in the solution phase. In the wherever you are actually putting or mixture of that, you are actually putting the cobalt that actually forming a different compounds. And with this, with the help of the CD spectra, we can differentiate that which one is the which. Okay, so today whatever we actually discuss, we have some discussion about that. We have our application of that CD spectra, how we can uh, differentiate, we can isolate the uh, protein structure from the different protein structure with the help of the CD spectroscopically. As we know, our protein structure has a four different structure. Four different structure. One is the primary structure, and there is a secondary structure, tertiary and quaternary structure. In that protein, we are able to find the my CD activity with respect to the N to pi star transition, N to sigma star transition, as well as the N to pi to pi star transition. But more interestingly, one thing is that we have our transition of N to pi star transition. We have the pi to pi star transition. All those transitions are chiral. Now question is this chiral? All those transition chiral? See, in the amide bond, there is a plane over here. This is the planar structure. Amide, this is amide. It is a planar structure. If it is planar structure, then there will be a chances of my uh, passing through a plane, sigma plane. If sigma plane is there, there should be achiral in nature. This amide bond should be achiral in nature. So my N to pi star transition or pi to pi star, this C double bond O, a pi to pi star transition also achiral in nature. But how it becomes chiral? So now answer is that yes, there is a chances of inducing chirality. So my here carbon, one carbon over here, the from the alpha carbon of the acids which is in chiral, they actually inducing some chirality into this amide bond. As a result, it will actually showing the chirality of the my peptide bond. In the secondary structure, we have we have defined chirality because of alpha helix. It's ill as a helical structure. If it is a helical structure, it's N2 pi star transition. Also here, the N2 pi star transition to define kind of N2 pi star transition in alpha helix has been present, and all those has a different magnetic momentum with respect to the my CO amide to hydrogen, amide hydrogen is N hydrogen and the CO of the 6 carbon over here. So that's why we have some induced chirality inside the this amide bond. But although my amide is the planar structure, the alpha carbon actually playing a crucial role. In the beta sheet also, this is induction happen in the beta sheet, but in alpha helix, helix itself as a helical structure. It also show the overall structure will be the chiral, 2D structure will be the chiral. Furthermore, my this amide bond actually induced by the next carbon, that is the alpha carbon of my my amino acids. That is the major fundamental things. Although my amide is the achiral in nature, amide bond should be achiral in nature, but due to the induced chirality next to the carbon, next to the alpha carbon, which is actually provide the chirality into the amide bond. Okay, and then we actually show the how the alpha helix, what is the characteristic of the alpha helix in the CD spectra and UVVs as well as. So in the alpha helix, we have the one pi to pi star transition around 193 nanometer region, and which is so the CD activity around positive direction. Sorry, and and two N2 pi star transition because of the two defined amide, two different hydrogen bonded amide present in the alpha helix, and which is actually around 208 and the 20222, which is all two bands are in negative region. In the beta sheet, there is a characteristic peak of N2 pi star transition is around broad 218 nanometer region, and that should be a negative. And the 195 by 2 pi star transition is a positive. The random call, initially they have some defined positive value, that is the around 200, beyond the 220 nanometer region to 200 nanometer region, near to the 210 nanometer region, there is a positive hum over there. That's always not be possible. And there is another possible possible is that the random coil has the N2 pi star transition always be at pi to pi star transition around 195 nanometer region, and the into pi star region, into pi star will be around positive direction. The reverse of the near to the beta seed, reverse to the beta seed, but not exactly reverse. Okay, so then we are able to calculate with respect to the initial original data, because of the we know the how the alpha helix, only the alpha helix can behaves in a CD spectroscopically, and CD spectra, beta seed as well as, and the random code. With respect to their original data, we can calculate, deconvolute the amount of alpha helix, beta seed, and the random coil present in the one particular amino acid. We show some example over here: myoglobin, lactate dehydrogenase, cytochromase, and Brin's genes of chromatopsin, and then Benz Jones proteins. Okay, and they also show different uh, alpha helical structure or beta sheet structure in that different pH also. Let's suppose we have the polylysine over here in the pH 7. They are actually showing that there is no zero alpha helix present. Only beta sheet, 100% beta sheet is present. Okay, in the polylysine, whenever the polylysine where the pH is 11.1, it's showing this polylysine actually showing the 100% alpha helix. So if you change the pH, the secondary structure of the my protein changes hugely, and CD Spectra actually monitor that phenomena. Okay, and furthermore, the protein denaturation with respect to the different pH as well as the different temperature can be monitored by the CD spectroscopy. Further, there is a we discuss about one example where the cobalt histidine molecule where this oxygen sensing happens. If oxygen sense oxygen actually bound with the cobalt deoxycobalt histidine complex, it show a different UV band where the DD band cannot be visible in the, but CD you can find it very easily, and the structure hugely changed in the CD spectrum in the CD band. Now there was another example where we found that we have a cobalt disuccinate complex, which is actually forming with RR isomer and the SS isomer differently, and which cannot be isolated by the UV spectrum. But in the CD spectra, where these two isomers can be easily isolated in the cobalt complex form. And with respect to it, we right now we are going to conclude over here. Next class onwards, there will be some other example of the CD spectra. If you have any doubts, please feel free to comment on my YouTube channel, or you can join the class and discuss among ourselves. We'll try to figure it out your problem. If you found any problem in the CD spectra, and we'll try to bring some questions from the gate or name. If there is possible, then next week we'll provide some examples over there. Okay, to it, I'll stop over here, and I'll upload it into the YouTube channel, all those video recording and all those notes, and we'll find it in that Google Sheet, whatever they are actually providing to us and to you also. Okay, by then we'll stopping over here. Let me finish saving. Okay, that's all. Save it and stop the sharing. Okay, so right now no one actually entering into the class. It's very difficult to always talking in front of the computer is very difficult. We'll try to figure it out. If some people can join, there will be some interaction session. So if they can interact, I can able to understand what are the problem you are facing right now, and we'll try to figure it out the problems. If you don't want to join, so you can find the recording class. After this session, I will upload it into the YouTube channel. I will provide you the link of that YouTube channel. If you have any queries, just write comment on the YouTube channel. Otherwise, you can join in the next class. We'll figure it out. Okay, okay, to that I'll s- stop over here, closing down over here. And thank you, class. We'll meet you in the next class. So in that time, I will be in Paris. From there, I will take the class. We'll join the class, and we'll discuss about that next class. Okay. Bye, bye, class. Thank you. I have to stop the recording first.